Okay, in the past couple videos we've been talking about ionic compounds and how to name them. We talked about transition metals and their Roman numerals. Now we need to talk about the idea of polyatomic ions. These are essentially molecules with charges. So instead of having individual atoms that have charges, we have molecules that have charges. There are literally thousands of these. I'm going to need you to memorize 8 of them. So here are the list of what I need you to memorize, okay? They are typically non-metal compounds that either have, most of them are nonmetals with a bunch of oxygens attached, or they're nonmetals with a bunch of hydrogens attached, and they have a name for the molecule, but they also have charges, so I'm gonna need you to memorize the structure, or like the formula, the name, and the charges. Sorry. We will get lots of practice of this. I promise it's not as impossible as it sounds. I will also tell you these polyatomic ions never go away. You will see them all through Chem 1 and Chem 2. I'm only making you memorize the 8 most common. I promise there are way more than this. So, most of them are negative. This is the one exception. So if you have a nitrogen with 4 hydrogens attached, it'll have a positive 1 charge, and this is known as ammonium. By itself, it's referred to as ammonium ion. We're gonna see it as part of ionic compounds. But this whole thing is, just to visualize it, this is a nitrogen with 4 hydrogens attached. And we haven't learned how bonding works, don't worry about it for right now. The whole thing altogether has a +1 charge. We don't care which element has a +1 charge yet. Eventually we'll learn that, but just visualize it as a nitrogen with 4 hydrogens attached ends up having a plus charge, and we can visualize it as an ion for our ionic compound naming, okay? It's the only one that's positive that we're gonna worry about. Most of them are negative, okay? So, and most of them are a non-metal with a bunch of oxygens attached. So a nitrogen with 3 oxygens ends up having a -1 charge, and this is nitrate. If you have a sulfur with 4 oxygens, it has a -2 charge, and this is sulfate. A carbon with 3 oxygens and a -2 charge is carbonate. A phosphorus with 4 oxygens and a -3 charge is phosphate. You'll notice that basically you just take the name of the nonmetal and make it an 8. Figuring out how many oxygens and the charges is kind of the hard part. I'm gonna need you to kind of memorize those. I'm sorry. We will get lots of practice, we will learn these, okay? There are 3 others that I'm gonna need you to memorize. We'll probably encounter others throughout the lab and lecture, but these are the ones I need you to memorize, okay? OH minus is hydroxide. It stops with the 8 thing, unfortunately, but this one is really common. Anytime we talk about acids and bases, anything that produces an OH, if you put it in water, is a base, so hydroxides come up a lot in chemistry, okay? One that's not as common, but it's worth mentioning, is cyanide. Okay. The last one I'm gonna mention is a little weird. It's actually an organic compound, so the structure looks a little different. This is acetate. Okay. If you had another H there and no charge, this would be acetic acid, which is what vinegar is made of. So this sounds like it's some weird, obscure compound. I promise it's not. I write it like this. Occasionally, you will see some textbooks write it like this. Actually, some of the labs write it like this. I don't care which way you write it. I promise I am going to write it CH3COO-. I taught enough organic chemistry in my life to realize that this makes more sense than this. Okay? So these are the ones I need you to memorize. In terms of how to use them, it's really not much different than we were already doing. You just incorporate them as a cation or anion as needed. So for example, if you had something like calcium and a hydroxide, if you needed more than one of any of these, you have to put parentheses around it to indicate that it's 2 of the whole ion. Instead of just 2 of an oxygen with 2 hydrogens, it's 2 of the OHs. But in terms of naming, we still name it cation and anion. So Ca is one that we can predict. It's in the second column. Its charge is +2. This would be calcium. And this one, if we memorize it, we know the charge is -1. This is hydroxide, so this is calcium hydroxide. Still the same naming scheme. We don't change any of the endings up here. This is already in the format that it needs to be. Okay, and we wouldn't even have to do anything else extra here. We don't need a Roman numeral or anything, but I'm going to prove that the charges work out. Calcium is in the second column, so its charge is +2. Hydroxide is -1, and we have 2 of them, so that would be -2. Okay, let's try a few more here just to get some practice. What if we have FeSO4? Okay, Fe is iron. It is one of the ones that we can't predict because it's in the middle, so we are going to need a Roman numeral. The Roman numerals do not go away just because of polyatomic ions. And then SO4 is sulfate. The S with the 4 oxygens all together has a charge of -2, and there is 1 iron to cancel it out, so its charge is +2. So the answer is iron 2 sulfate. Okay. Let's try a few more here. PbCO3 2. Pb is lead. It's under the stair step, so we can't predict what its charge is. So it's lead, some sort of Roman numeral. We'll have to figure out its charge here in a minute. CO3 is carbonate, and it has a -2 charge. So this is still just carbonate. In terms of figuring out the charge of the lead, carbonate has a -2 charge, and we have 2 of those, so that's -4. So lead would have to be, and there's only 1 lead to cancel it out, so lead would have to be +4 to make that balance out. So this would be lead 4 carbonate. Okay. You see that the Roman numeral thing and the polyatomic thing actually combine together. Neither of the rules change when you do that, but both ideas get smashed on top of each other. Honestly, if you look at the number of metals that we know versus the number of metals we don't know, ones with Roman numerals are actually the more common answer. And honestly, in terms of anions, it turns out that polyatomics are the more common answer. So this is actually most likely to come up in the real world, is things with Roman numerals and polyatomic ions. Let's try at least 2 examples going the opposite direction, where we have the name and we have to figure out the formula. Okay, let's go with aluminum nitrate. Okay, aluminum is one of the only ones that we can predict. If you look back at the notes, we said this is column 1 is +1, column 2 is +2, and aluminum is the only other metal we can predict, and it's +3. So this is going to be Al, and it's going to have a +3 charge. Nitrate is one of our polyatomic ions. It's NO3. And that N with 3 oxygens attached has a -1 charge. So that's -1. So we're basically going to need 3 of these to cancel out the aluminum. Aluminum doesn't get a Roman numeral because we know what its charge is. Okay. Let's try one with a Roman numeral in it just to see how this works. Okay. Let's go with molybdenum, which is kind of a weird word to spell. Molybdenum 3 acetate. Okay, this time we do have a Roman numeral. We do also have a polyatomic ion. Molybdenum is in the middle here. It's one of the ones we can't predict, but that's fine because we know the Roman numeral. So, because this is a 3, this is going to be +3. Acetate is CH3COO minus. It's going to have a -1 charge. So in terms of writing this out, molybdenum is MO on the periodic table, and acetate is CH3COO. This is +3 and -1, just like this one was, so we're going to need 3 of that entire thing to cancel out the molybdenum. Okay. If you can get this much, I'm happy. I'm going to actually draw what this looks like so you can kind of see how this is as much as this sounds complicated, this is actually the simplified version of this. So molybdenum would have a 3+ charge, and acetate is a complicated looking molecule. It has a double bonded oxygen there, then an oxygen with a negative charge, and then has a carbon with 3 hydrogens sticking off. And there would honestly be 3 of these. And I'm kind of shortcutting some things here, but that's okay. Running out of space. But this is what it looks like. This looks super messy, but in the real world, this is what the molecules would look like and how they would stick together. I do not need you to draw this. I need you to be able to give me the formulas like that. At some point, we will learn how all these structures work, but that's way down the road, okay? We will definitely see more examples of this. I'm gonna at some point put together a practice worksheet on OnCourse for you to get more examples of this and more practice of this.